Hello, this is Concrete Path and the lecture for your third method of the stress calculation for your pre-stress concrete. For your pre-stress concrete, that's what we call as strength concept. Strength, strength concept. We can also call it as internal couple method, internal couple method, internal resisting couple. Okay, we can also call it as P line, or we can also call it as C line, or we can also call it as thrust line. Thrust line, or P line represents that pressure line, and C line represents that C force line. That is the same thing we say by different names. So let's go for that method. Let's go for that method. So this is the third method for calculations of those stresses on the section. I would say you take a bent cable. Let's take a bent cable. Let's take a general beam with a cable that's bent. Okay. So it's having some eccentricity from the neutral axis. That's E1 and E2, E1 and E2. So E1 is above the neutral axis. At the ends, we say E1 is above the neutral axis, and your P force is acting along the cable. Okay. Now we are going to say your eccentricity of the cable is E1 at the ends and E2 at the midspan. Okay. Now we would say what this C line, P line represents, what it is saying. So at any section, you take any section at any location X. Let's take any general section. Let's take any cross section. Let's take any cross section somewhere at a distance of X. So let's say this is your location of X, and at that location I would say we will call this part as EP. That eccentricity of that P force, I would call it as EP. And if we take the overall that triangle, bigger triangle we have, overall bigger triangle we have. So let's take it outside. Let's take this triangle outside. Let's take this triangle outside. So we are having some E2 here, and up somewhere we are having that value of E1 also. So I would say the total value is equals to E1 plus E2. Okay, and somewhere it's cutting that line. Then I would say your EP is somewhere here. That is, this is your length of X. Somewhere you are cutting this section such that this part is your EP and this part is your E1. This part is your E1. This part is your E1. And total length is L by 2. Total length is L by 2 from this side. Total length is L by 2. So we are cutting this part. We are taking this part outside. We are taking this part outside. So 0 is somewhere here. So this is your 0. After that, we are going to say what is this value of EP? Can you say that your total value of Y, your total value of Y, that I would say total value of H is E1 plus E2. Total value of H is equals to E1 plus E2, and E at any P is equals to location of that E at any P would be equals to, it can be solved from the similar triangles. Let's see how we are going to solve that by the similar triangles. We need to calculate that eccentricity of that point P at that section. Let's solve it by the similar triangles. I would say E1 plus E2 divided by L by 2 is equals to E1 plus EP divided by X. So we can get the location of EP. What is the value of EP? Okay. So finally, so we need to say what is this thrust line, P line? We have touched it in the first lecture that the C line represents that that locus of resultant of that C force, locus of resultant of C force on that section, on sections along the length of the beam, on sections along the length of the beam. So we have already taken one problem for that to calculate the line, C line. So that was some sort of line was formed. Some sort of line was formed when we take those sections of 0 meter, 3 meter, and midspan. So our values were somewhere here, here, and here. So that curve was formed. That locus we joined. We said this is your C line. This is your C line. We can also call it as pressure line, or we can also call it as thrust line. Thrust line. And we said that there is a concept of internal couple also there. That means at any location, at any section somewhere, at any section somewhere, at a location of X, we would say there is some eccentricity of that load P, pre-stress force P, from the neutral axis, as we wrote that as EP, and we said that because of those bending stresses, our net value of that stress diagram was some. Let's take some general value. Let's take some general diagram, and we said there is some compressive force acting somewhere at some location of X bar, such that we calculated that location of that centroid. After that, we said, let's say centroid is acting somewhere here. Let's say centroid is acting somewhere here, and we call it that this part as lever arm, and this was equals to EC plus EP, where your EC was equals to Z minus EP.
Okay.
So then after that, we said the moment, the internal moment because of this couple is equals to P times Z or C times Z. And we were able to calculate that this moment, we had checked that moment was coming out to be moment at that section, because of external loads. So this is the start of that problem, that how we are going to solve this problem, how we are going to calculate the stresses based on this method. So this all we are saying, it's all based on the first lecture of your RCC. You can check that also. So let's take that accordingly. That the first step is that you have a section at any location X. As that of this case, we take any section at that location of X. I would say the eccentricity of the cable is some value of EP. So here the eccentricity of the cable is some value of EP. Okay, some value of EP. Okay, then I would say that's resultant would be somewhere. Let's say that resultant of that entire thing is somewhere here. Resultant of that that stress diagram is somewhere here. This stress diagram, let's write it. This stress diagram, this is the stress diagram because of stress diagram because of because of because of because of all those combined factors. One was your P by A, second one was your PE by Z, third one is that M by Z. This is also M by Z. So based on that, we had some C force acting here, and this is your C force. That was also equal to P force. C force equals to P force. I would say this part is your EC, and total part we can call it as Z. So the first step in the calculation of this method, that is to calculate that Z bar. So this Z bar, that we call as shift of uh, P line, or we can call it as C line. Shift of P line or C line from your cable line, where your cable line is the line where or point where your P force was acting, So your P force was acting at EP. So that's what we are calling it as cable line or cable point, we can say. So that is the shift of that P line. That means this is the shift. So initially your P line, yeah, your P force was acting here, or we can say cable line was here, but your C line is somewhere here, or we can say P line is somewhere here. That is the pressure line, or we can say thrust line is somewhere here. So it's at a distance of Z. So that we call as Z, and that can be calculated as Z is equals to moment at that section X. I would say this is the bending moment at that section X because of the external loads. We had to solve external loads. Why we are going for external loads? Because this why we have already touched that in the first lecture. You would see that. So this is your moment at X divided by pre-stress force of P. So this is the first step we are going to perform. Z is equals to mx by P. And second step is that P is also equals to C. Okay. Second step is that once we got the Z location, and second step is that uh, this Z value will tell me that from the with respect to P line, why are your with respect to your P force, with respect to your P force, where your C force is acting. With respect to P force, your C force is acting. It can tell me, and based on that, I can get the value of EC. So second step is that you get the value of EC. Second step is that you get the value of EC. Get the value of EC, and for that you can say uh, from this perspective, if you take this part, if you take this section, I would say your EC can be solved by that. I would say Z minus EP. So EC can be solved as Z minus EP. Let's take a general formula for that, and it depends on the values of that values of Z. So accordingly we can have that EC value. So let's say that Z was that we have Z minus EP. Okay, once we got the EC value, then we say we are going to perform that third part, that is calculation of stresses. So I would say there is some force, there is some C force acting, there is some C force acting somewhere here at some location of EC, at some location of EC such that my stresses are C by A, and one more stress is that we call as CEC by Z. CEC by Z. And that's all. In this case, in this method, we are not going to take the moments, external moments, M all by Z. We are not going to take this part. We are not going to take this part. It's already accounted. It has already accounted in the calculations. It has already accounted into the calculations in the calculations of EC. That's why we are taking that Z equals to M at any section X and divided by P force. Actually, this MX has been developed because of those bending stresses that has developed on that section. So I would say this part is not accounted. Only two diagrams we have to take. One is your C by A. Next one is that CEC by Z. CEC by Z. So this is your third method, that is strength method. So let's take a problem that we can understand. So let's take a problem that let's take a first problem. Let's take the first one that we can say that so we have a beam, and it's having subjected to it is subjected to live load of what is the live load intensity? 15 kilonewton per meter. 15 kilonewton per meter. It is simply supported, and we have 8-meter beam, 8-meter length, and the eccentricity of the cable is 0 at the ends and 200 at the midspan with respect to the neutral axis. So your P force is acting along the line of that cable. P force equals to 1500 kilonewton. 1500 kilonewton. And if I take the cross section, if I take cross section of the beam, is that we have 750. Depth of the beam is 750 and width of the beam is 400. And we need to say what is the we need to say find the location of thrust line. Find the thrust line location. And we have to use that stress concept. First method, stress concept. Second method is that strength concept. So we had to use both the methods. And then after that, we need to calculate at the midspan. We have to calculate at the midspan stresses at the midspan using the strength concept. So third part is that you have to calculate stresses at top and stresses at the bottom on the midspan section using strength concept. Midspan section on using strength concept. Okay. So let's try to get the problem. Let's try to take the problem. I would say, based on the stress concept, we need to calculate the location of the C force. We need to calculate the location of the C force. Okay, let's try to get that. I would say we have three kinds of forces. One is that we have to calculate stresses at the midspan. Stresses at the midspan. So I need to calculate what is the eccentricity at the midspan. Can you tell me what is the eccentricity at the midspan? So this is we are calculating for the midspan section. So at the midspan we are having a beam section such that the eccentricity at the midspan is, this was given to you, 200 millimeters. So I would say it's acting somewhere here at some eccentricity of 200 millimeters. So this P force is acting. So I would say the stresses at that midspan section would be equals to plus P by A. And second one is that PE by Z minus plus PE by Z. And third one is that because of the moments. Can you calculate the dead load? W dead is that 24 into 0.75 into 0.4, or we can keep 25 also. It depends. Usually we would take 24 into 0.75 into 0.4. That's 7.2. We're going to calculate for 24. So that's 7.2 kilonewton per meter. And that means the total load, that means that the M all, I would say, moments because of all those UDLs, that is equals to 22.2 L square by 8. That is equals to 177.6 kilonewton meter. And because of this sagging moment, we are having some top compressive, bottom tensile, top compressive, bottom tensile, top compressive, bottom tensile. So this is M. Let's write the value, 177.6 kilonewton meter divided by Z. So we have three different stresses based on the stress concept. We had to calculate based on the stress concept. So this is the stress concept. Stress concept. So let's solve those values. Let's get those values. 1500 is your 1500 is your P force. 1500 kilonewton divided by area of the cross section, 0.4 into 0.75 meter square. Then your P by then your P into E. Value of E is 200 millimeters, and section modulus is 0.4 BD square by 6. BD square by 6. And third one is your 177.6 divided by BD square by 6. BD square by 6. So those values can be solved, and you would get the stresses. I would say stresses at the top is equals to P by A minus PE by Z plus M by Z. And stresses at the bottom is P by A plus PE by Z minus M by Z. So only the sign is changing here, except for this one, P by A. Okay, now I will calculate those values, and they are coming out to be equals to the overall values is coming out to be equals to 1.736 megapascal, and this one is your 8.264 megapascal. So let's have the stress diagram. I would say this is your line, and 1.763, 1.736, and second one is that 8.264, and you join them by straight line. You join them by the straight line. Now I need to say this is all compressive stresses that have developed on the section because of the resistance of the section. So I would say the centroid of the overall stresses that's making a force of C. That is the average stress into area of the cross section of concrete on concrete. This is for concrete. So average stress is that 1.736 plus 8.264 divided by 2 into the area of the cross section. Area of the cross section is 0.4 into 0.75. This is the area of the cross section. So you can get the stresses. You can get the total force of C equals to that should be equals to P force. Let's see whether this value is equals to P force. 1.736 plus 8.264 divided by 2 into 0.4 into 0.75 is equals to 1.5. So 1.5, that means 1500. So this is 1500 kilonewton. 1500 kilonewton, that means that's also equals to P force always. This is always equals to P force. So once I got the C force, and the problem was saying that you had to calculate the thrust line location of that thrust line. That means I got the C force. I need to say now where this C force is acting. That means the location of that thrust point. So I would say from the top, let's try to calculate from the top that it is somewhere here at y bar. So y bar can be calculated as 1.736 plus 2 times 8.264 divided by sum of these two stresses, 8.264 into total width. Total depth was 750 divided by 3. So this value is equals to 456.6 millimeters. If this is 456.6 millimeters and total cross section depth is 750, that means 456. That means it's below the neutral axis. C force is below the neutral axis somewhere here. Can you say that? C force is below the neutral axis somewhere below. That means if this is 375 out of the total 750, that means your y bar is somewhere here. Y bar somewhere here. So this should be your C force location. So that y bar is equals to 456.6 millimeters. So this was the part one. Now we need to say from the second method, we need to calculate the thrust line location based on the second method, that is strength concept method. So if I calculate by the strength concept method, what it says, its first step is that location of that thrust line is that Z, we represent that as Z, or this is, we can say this is the CG of C force to CG of P force to CG of P force. That is also called as shift of the P line from the cable line. So we can write that Z is equals to moment on that cross section, moment on that section. This is bending moment on that section because of external loads divided by pre-stress force P. Now we need to say what is the bending moment at that section. What is the bending moment at that section? Is that this one because of the external loads 177.6. So if I take this value 177.6 kilonewton meter and divided by the pre-stress force, your pre-stress force was 1500 kilonewton. So this value is coming out to be equals to 118.4 millimeters. So this means that you had this section, you had this beam section of B cross D. So this is your neutral axis, and P force was acting somewhere here. This was your location of P force, and the total value was, we call it as EP. It was for the midspan section. It's for the midspan section. We are calculating for the midspan section. At the mid we had EP equals to 200. From the diagram we can see your EP at the midspan was 200 millimeters. So we need to say where your C force is acting at that midspan section based on the strength concept. So we got the value of Z equals to 118.4. That means you have to go from you have to shift your point from the P line, that is from the cable line. This is the cable line, I can write here. From the cable line I had to go 118.4 above, 118.4 millimeters above, such that there is some force C. There is some force C acting. So somewhere here. So somewhere here your C force is acting. Thrust line, or we can call it as cable line. Sorry, thrust line, pressure line, C line. This is your C force or C line, C force. So can you tell me now what is the value of EC? Can you tell me what is the value of EC now? Can you tell me what is the value of EC for this case? Is the value of EC this part? So your EC would be equals to Z minus EP. Let's see what this value can be. Z was your 118.4 minus your EP was 200. So we got a minus value of 81.6 millimeters. That means negative means it is below the neutral axis. This equation we have used this equation based on the fact that we said C force was above and P force was below, and based on that we said this is your Z, this was your EC in the previous case during the derivation. But in this case I would say EC can be solved as 200 minus 118 By the physical observation, I can directly say this is 200 minus 118.4, that is 81.6 below the neutral axis. Okay. Now third part of the problem is that you have to calculate the stresses at the midspan section using the strength concept. So that means once I got the value of EC, I had to calculate the stresses on that midspan section based on the concept of that C force. Let's say that this is your section and this is your neutral axis. Your EC value is below the neutral axis. Your EC is below neutral axis. Can you see that? Your EC is below neutral axis. I would say there is some C force acting. So on this section, C force is acting at some eccentricity EC. Okay. So let's go for the stresses now. Let's solve for the stresses based on this method C force method or strength method. So I would say there is some force of C by A, and there is one more moment, one more force, one more stress because of that CE. See, your C force is below the neutral axis, so it would create hogging moment on that section. So your stresses would be top compressive, but yeah, hogging means top tensile, bottom compressive. Top tensile, bottom compressive. Top tensile, bottom compressive. So this value is CEC by Z, and top is also CEC by Z, but your top is negative, bottom tensile compressive, positive. So we can solve all in these two. We don't have to account the moments. We don't have to solve for the moments in this method. So I would say your C force is always equals to P force, and that means 1500 kilonewton divided by area of the cross section. Okay, and plus, and this is your stresses at the top. And plus I would say minus, because at the top we have negative. CEC by Z. CEC. Value of EC we calculated as 81.6. 81.6. So 81.6, we can write in terms of meters, 0.0816 meters by Z, section modulus BD squared by 6 meter cube. So you can solve that. The stresses at the top would be equals to exactly as that of a previous method. That's 1.736 megapascal. And second part is that stresses at the bottom, that is C by A plus CEC by Z. C by A plus CEC by Z. C by A plus CEC by Z. Okay. So that value is equals to 8.264 megapascal. And that's value. These two values are earlier we have already got these two values based on the stress concept. Based on the stress concept, we already got these two values here. You can see. So that was the problem that we have. We can take one more problem, that band cable. Let's take a band cable. Let's take a band cable that let's take a band cable. This is your beam, and it is subjected to a UDL. There is a UDL, live load 40 kilonewton per meter, and a point load is also applied at the midspan. Point load at the midspan equals to 100 kilonewton. And we need to calculate stresses at the 4-meter section. So stresses we need to calculate at the 4-meter section. So at 4 meters we need to calculate what is the stresses at that location, at that section, somewhere here. So your total length of the beam is 12 meters, and it is simply supported Prestress beam, PSC beam. And the thing is that the cross section we can show. There is a cross section. This is your cross section, and the dimensions of the cross section is 600, and depth is 900. 900 millimeters. And the cable profile is that your cable is a straight line profile. That's a bent cable. You can say this is a bent cable, and it's having eccentricity 100 and 200. 100 and 200. If there is a neutral axis somewhere, let's say there is some neutral axis. This is your neutral axis, and what you call as cable is having some eccentricity at the top, at the ends, and at the midspan. So cable is in this fashion. Okay, so this is your cable, and eccentricity is provided to you as the value of eccentricity. This value is equal to E1. E1 is equal to 100 millimeters, and E2 equals to 200 millimeters. 200 millimeters. Okay, and the force is applied on this beam, on this cable. P force is applied, and your P force is equals to pressure force. Prestress force is equals to P naught into area of the steel. Stress in the steel wires into area of the steel, and I would say that data we can solve directly. That we have this data of 1500 megapascal of stress in the steel wires, and area of the steel wires is equals to 2700 millimeters square. So overall P force that has developed on the concrete, that is equals to 4050 kilonewton. 4050 kilonewton. Now we need to say what is the stresses at this location. What are the stresses at this location at 4 meters from the end side. So I would say you can solve, you can calculate. Basically we have to solve it by all those methods, by all three methods. So you need to calculate stresses at the top and bottom on that 4 meter section, F top, F bottom, using all those three stress methods. One is your stress concept, second one is your load balancing concept, third one is that strength concept. Okay, let's take one by one. Let's go for the first one, that is strength concept. Strength concept. Okay. Strength concept. And for the strength concept, so if we are calculating for the first case, that is strength concept, if I'm calculating for the first one, that is stress concept, it needs the actual location of EP. Stress concept needs actual, it talks about particular section, and it is actual EP location, it is actual P force. It talks about actual EP, actual P force, actual moments on the section. It talks about all those things. So we need to see at this section, that is at 4 meters from the end, we have to say what is the value of E at that location. E4 I would call it as, or we can say this is EP. What is the location of EP? And there is some P force there, and we need to say what is the moments at that location for M4. We need to solve these data for the stress concept. So I would say that if I take this triangle, similar to what we have derived earlier, if I take this triangle, I would say we have some eccentricity of E1 plus E2 for the bigger triangle. We have this eccentricity of E1 plus E2 for the bigger triangle for the length of L by 2. Your L by 2 is equals to 6 meters. And I need for the 4 meters. Somewhere here. What should be the value of EP? So I would say that E1 value is somewhat in this, that this is your E1 value. If this is E1, this is also E1, and there is some value of EP at that location. Can you tell me what is the value of EP at that location? If the E1 is 100, E2 is 200, can you tell me, based on the similar triangles, I would say 100 plus 200 for the length of 6 meters, but I need for the length of 4 meters, and we have E1 plus EP. That's E1 is 100, so I can solve EP equals to EP would be 100 millimeters positive. That means below the neutral axis. So your EP value is 100 millimeters below the neutral axis. So that's by symmetry we can say overall is 300. At 4 meters it would be 400, and here it would be 200, and here it would be 0. So we got the final value that this is 200 below the neutral axis. So I can solve by the stress method now. I would say you had this section at the midspan. At this section, what you have at 4 meters, we had this section, and from the neutral axis we had to go value of EP equals to 100 millimeters below the neutral axis, such that your P force is acting there. And I can draw the stresses now. P by A, and negative positive, negative positive, negative positive P E by Z. And third one is that because of the moments at that section, that would be sagging, so I would write plus minus M4 by Z. Let's solve for the values of M4. Let's go for the value of M4. Let's go for the value of M4. Can you calculate the value of M4? Can you calculate the value of M4? You are having a point load, you are having a live load, you are having a dead load also. Dead load would be solved as gamma of concrete into area of the cross section. So that's gamma we can take as 25 kilonewton per meter cube, and your 0.9 into 0.6. So you can have this value equals to 13.5 kilonewton per meter. So can you tell me what is the reaction at the support A? Vertical reaction at the support A? That would be 13.5 plus 40. This is the total UDL we have, and into length of total length was 12 meters. So I would write 12 meters by 6, 12 meters by 2. So this is the reaction A because of the UDL, and plus your 100 kilonewton is distributed because it is at the midspan. So it's, I would say 100 by 2 is taken by the support A. So this is the reaction A. I want the moment at 4 meters. I want the moment at 4 meters. So I have to multiply that 4 meter. So let's calculate the reaction A first. Then after that we can have it easily. I would say 50 plus 6 times 53.5. So that's 371. So your reaction is equals to 371 kilonewton. So now can you tell me what is the bending moment at this section M4, which is having some UDL and which is having some reaction of 371? Okay, I would say the total UDL here is 53.5, and total length for the section is 4 meters. Can you calculate the bending moment at that section? And that M4 would be equals to 371.4. Yeah, 371 into 4 plus 53.5 into 4 square by 2. So that M4 is equals to, M4 is coming out to be equals to M4 1056 kilonewton meter. 1056 kilonewton meter, and that is positive, so we would say top compressive, bottom tensile. 1056. So this is your 1056 kilonewton meter by section modulus. Your section modulus was BD square by 6, BD square by 6 meter cube. And similarly this one would be solved as your P value. We calculated the value of P. Do you got the value of P? We have solved the value of P. The value of P was somewhat 4050 kilonewton. 4050 kilonewton. But the thing is that your force is not purely straight. It's not perpendicular to the cross section. Your force is not perpendicular to the cross section. If you take that section, is your force perpendicular to the cross section? If you take that section at the 4 meter span, this section at the 4 meter section, you are applying the force in this direction, in this way. This is not purely vertical, so I had to resolve it. I would say the vertical component of your horizontal component of the force would be P cos theta. This is some theta. So this is some P cos theta is applied here. So we need to calculate the theta here. I would say there is some theta. We are having some theta, and then that theta can be solved in this triangle E1 plus E2 for the length of L by 2. We had some theta. Cos theta would be equals to E1 plus E2, 100 plus 200 divided by total length of L by 2, that is 6000 meters, 6000 millimeters. So your cos theta is very less value, still we can calculate that. still we can calculate that. Yeah, this is your tan theta, sorry, this is your tan theta. Your tan theta, then finally I would say theta is coming out to be equals to 2.864 degrees, and your cos theta is coming out to be equals to some value. We can check that. Cos theta, cos of theta, that is 2.864 degrees, and this is 0.9988, so it's almost equal to the 1.9988. If you still want to calculate on this value the stresses, let's try to calculate on this value, p cos theta 0.9988, 0.9988. That means I have to solve for the values of p cos theta, not the values of p. If you want to go for the actual calculations, I would say your horizontal force, that is actually p cos theta, so your stress would be corresponding to p cos theta, p cos theta, p cos theta. Okay, now p cos theta would be equals to 4050 was your value of p, 4050 kilonewton was your value of p. Then cos theta, when you multiply it, this value is coming out to be equals to 404045. So only a difference of 5 kilonewton, 4045 kilonewton. So if I solve now, p cos theta by a, this would be equals to 4045 kilonewton divided by cross section area 0.4 into 0.6 into 0.9, 0.6 into 0.9. And second one is that 4045, your eccentricity EP, we calculated the value of EP at that 4 meter section, EP 100 millimeters below the neutral axis, so 0.1 meters divided by BD square by 6, BD square by 6, BD square by 6. And third value we have already calculated that. Now we need to say what is the stress at the top and bottom. So I would say the stresses at the top would be equals to F top, that is plus, yeah, this is plus, and second one is the minus, second one is minus, after that third one is the plus, and F bottom would be plus, plus and minus, m by z. So based on those two, we can get the values that F top is equals to 15.53 megapascal, F bottom equals to minus 0.552. So the variation would be somewhat in this way. So this is our stress variation. This is our stress values based on the stress concept at 4 meters from the ends, from 4 meters from the end. Now second method is that load balancing concept. Let's go for the load balancing concept now. Load balancing concept. Load balancing concept. Load balancing concept. Load balancing concept. So what load balancing concept says? So it says that it's from the question, it's saying we have a cable, that's a bent cable, that's a bent cable. So I would say if it is not mentioning that which of the cable should have, then we were having two different loads. One was your dead load, live load, and one was your point load. Then I would say which of the cable you should prefer. Either you should prefer parabolic, you should prefer triangular. But that was the question here. But the problem is saying directly that you take a cable that's a triangular cable. You take a triangular cable, then you solve for that stresses at the 4 meters, stresses at this location, on this section, 4 meter section. So I would say based on the load balancing concept, I'm going to have that balancing load corresponding to, because I have a triangular variation of that cable, I have to transform it into a straight line. That means I have to apply that 2p sine theta balancing load, 2p sine theta only. I don't have to go for 8p h cos theta by L square. I have to go for that balancing load of 2p sine theta. So that means your diagram can be modified. Your diagram can be modified in this way. So I would say you had the beam, and I would say the cable would remain straight line along the line of the cable, along the eccentricity of the cable, such that it's having same value of eccentricity throughout the length as it was having at the ends. So it's having eccentricity of E1 at the end. So I have to keep that eccentricity throughout the entire length of the beam. So I would say this eccentricity of the cable is E1 100 millimeters. So that's how we modify that load balancing by how we modify that loading as per load balancing concept. And there's some loading also. Let's say this is some dead load plus live load. This was 53.5 kilonewton per meter. This was 53.5 kilonewton per meter. 53.5 kilonewton per meter. Okay. And one more thing is that we should have some balancing load also. Balancing load corresponding to the vertical load. We have bent cable, so we had to say there was some vertical load 100 kilonewton, and because of that we had a cable that was having a bent shape. So because of the bent shape, now we had transformed that into a straight line, and we had to apply that balancing load of 2p sine theta at the midspan. 2p sine theta at the midspan. And we generally write that 2p sine theta is equals to 2p tan theta, but we can take the direct values of sine theta here. Let's solve the sine theta now. Sine theta. So sine theta would be equals to 0 0.0500. So this is our sine theta. And if I say what is the tan theta, tan theta can be solved as 300 by 66,000. So 3 by 60, I would say. Yeah, tan theta is also equals to 0.05. If you see that, tan theta is also equals to same value. Tan theta is also 0.05. For smaller values of theta, we have same, almost the sine theta almost equals to tan theta. So I have to take that sine theta value 0.05. Now if I say what is this value, what is this balancing load equals to? 2 into P. Your value of P was actually 4500 4500 4050, I think. 4050. What was the value? Yeah, 4050 4050 4050, and the sine theta 0.05. So overall value, I think, is 4050 into 2. That's 405 kilonewton. 405 kilonewton balancing load. So a net, I would say net value of vertical load is downwards. So net value of vertical load is downwards at the midspan, such that that value is equals to 405 minus 100. That is 305 upwards. Is it 305 upwards? I think it's 305 upwards. So I would say this is 305 upwards. This is 305 upwards. 305 upwards. 305 upwards. It should be 305 upwards, and we are having some UDL also downwards. We are having downward UDL of 53.5 kilonewton per meter, and we are having some simply support beam, and we are having some cable also, having some eccentricity of E1, eccentricity of E1, and the cable is having some P force. And I would say whether this value is P, or we can take it as P cos theta. What do you think? Is it P cos theta? I think it's P cos theta. So your horizontal load should be P cos theta. P cos theta. If you take that cable, it's having some component along x and some component along y, so this would be P cos theta. I would take that as P cos theta. So that means this is P cos theta. And we already know P cos theta was 40545 kilonewton. So let's solve now this problem, and we have to calculate that stresses at that 4-meter section. Stresses at that 4-meter section here. Stresses at this section that was at 4 meters for the total beam of L equals to 12 meters. So we need to calculate this stresses at that 4 meter. Can you now calculate the stresses based on the load balancing concept? Let's go for the calculation of moment. I need the moment at 4 m4. So can you calculate the reaction at A? Reaction at A would be 53.5 into length of 12 divided by 2, and this is upwards load, so reaction would be downwards. 305 into 12 by 2. Yeah, 305 divided by 2, sorry. 305 divided by 2. So this is the reaction at A. 53.5 minus 53. So this is 168.5. reaction of 168.5 kilonewton, reaction of 168.5 kilonewton. So that means moments at what you call as section 4, that's bending moment at section 4, m4 is equals to 168.5 into 4 minus UDL of 53.4 into 4 square by 2 into 4 minus 53.5 into 16 by 2, 246. So moments is equals to 246 kilonewton meter, 246 kilonewton meter. So once I got the moment, now I can say the stresses can be solved as that you had this beam, beam cross section, and there's some eccentricity of the load, that's P load. P is acting somewhere here, at some eccentricity of E1 such that the stresses would be plus P by A, compressive, direct compressive stress. Second one is that this PE would cause a sagging moment, so it would cause a sagging moment. So I would say top compressive, bottom tensile, and this should not be P, this should be P cos theta, let's write that this is P cos theta. So our values would be P cos theta, and this stress would be PE P cos theta E1 by Z, P cos theta E1 by Z, and third one is because of the moments, because of the external moments we have, plus minus, that's M by Z, that's M4 by Z. And let's solve the values. Now. So tell me the stresses at the top. That is P cos theta, that is 4045 divided by section 1 0.6 into 0.9. Second stress is that at the top we have positive, and positive, and positive, and positive. So second stress is that P cos theta, that is 4045. Eccentricity E1, that is 0.1 divided by section modulus 0.6, 0.9 square into 6 inverse. And plus third moment is that 246 kilonewton divided by section modulus 0.6, 0.9 into 0.9 square into 6, this one. So that stresses. And similarly at the bottom, can you tell me what are the stresses at the bottom? F bottom equals to plus, after that minus, so this you have to plus, then after that you have to minus, this is minus. So you got the values as stresses at the top is equals to 15.54 megapascal, and stresses at the bottom is equals to 0.552 megapascal, negative. This is negative stress, and top value is having positive 15.54 value, 15.54 and 0.552. So this is your variation. Stress using the concept of load balancing. So third method is that using the concept of strength method. So we have the third method, that is we call as strength concept. And you can see that stresses should be same, 0.552, 15.54, and you compare with the stress method. You compare with the stress concept, you can have the same stresses there also. So we'll be having same value of stress in all methods. So let's remove this now. We are going for the third method, that is strength concept. Strength concept. So third method is that strength concept. So in the third method, that is strength concept, we have to calculate. First step is that in the strength method, we have to calculate the shift of the P line from the cable line. Shift of the P line or P force from the cable line. Shift of the C line, thrust line, pressure line, P line from the cable line where the P force is acting. So that we represent as Z. That is actual moments on that section M4 divided by the pre-stress force you applied. So I would say because of this is M4 because of the external loads, only the external loads which are there, because of the external loads, and we have already calculated that earlier. We have calculated that. I think this one should be that. Once I got the reaction, actual reaction, because of the external loads, 100 was there, 100 by 2, okay, reaction correct. and total UDL, dead load plus live load, correct, and L by 2. Okay, total reaction we got. Now we need to say moment would be reaction A into 4, reaction A into 4, okay, reaction A into 4, and uh, this was clockwise, and this one should be anti-clockwise. This was clockwise, and second one should be anti-clockwise. So second one should be anti-clockwise because UDL is anti-clockwise and that upward load is clockwise. So 371.4 into 371 into 4 minus 53.5 into 8, that's 1056. So this was correct. So this is the correct value that we have to take, 1056 kilonewton meter. So 1056 kilonewton meter divided by pre-stress force of P. Prestress force of P. Now let's say that we are going to say that you take that section at 4 meters. Your P force is acting somewhere here. P force at some eccentricity of EP, we have calculated that was 100 millimeters below the neutral axis. We have calculated that EP was 100 millimeters below the neutral axis, somewhere here. This was your 100 millimeters below the neutral axis. And is it actually P force, or is it's P cos theta? I think it's P cos theta, because the cable is not purely horizontal. It's having some component along the horizontal direction. So the force normal to the surface, that's P cos theta. P cos theta. So I would say your P cos theta was actually 4045 kilonewton, and your P actual force was 4050 kilonewton, actual value 4050, and your P cos theta is 4045. Now based on this one, I got the value of Z. I got the value of that, what you call as, I got the value of Z that can be solved as M at the 4 meters bending moment at the 4 meter section divided by the P cos theta. I have to write here P cos theta. So that is 4045 kilonewton, and I can get the value of Z, and the value of Z would be equals to 261.06 millimeters, and we got this positive value. That means it's above the neutral axis. That means with respect to that P line, with respect to that P force line, it's above that P force line. If this is your P force point, above we have to go how much? 261.06. So somewhere we are going to reach here. So this is our line of action of that C force. This is our line of action of that C force. C line, I can say. So this point is your, and I would say, what is this value of EC? Now I can call it as EC, and our Z was your Z was this part. So I would say your EC is equals to Z minus EP, and I would say 261.06 minus 100 millimeters. So that is 100 minus that 161.06 millimeters, and that's above the neutral axis. So our calculations would be based on this actual C, actual EC values. So our strength concept is based on C force and its EC eccentricity from the neutral axis. So let's take that section now. I would say you have this section and you are applying some C force here at some eccentricity of EC, and the stresses would be developed as C by A, and second one is that C by A, second one is that CEC by Z. And because the moment about the neutral axis is sagging CEC, so positive, I would say bottom tensile top compressive, CEC by Z. And I would say C force is always equals to P force, but your P force here is P cos theta, so your C is corresponding to P cos theta. So I have to take the values. I would say 4045 kilonewton divided by area of the cross section. Area of the cross section was 0.6 into 0.9, and I am calculating for the stresses at the top. That is positive. C EC, your EC is 161.06 meters divided by section modulus of BD square by 6 meter cube, and you calculate those two values and you can get some value, and F bottom would be C by A minus CEC by Z. and those stress values can be calculated to final values of that stress top and stress bottom coming to be equals to 15.5 15.534 megapascal and minus times 0.552 megapascal. So I would say these two values we already got in other methods also. So that means either of the three methods you can apply to solve a particular problem. So this is our stress variation. And if I want to say I want to directly calculate the C force from this one that we already have calculated, I would say here the stress is 15.534 and the stresses here is 0.552. This is the extra part we are doing. I want to calculate the C force and its location. Let me get that C force and location of that C force. Let's try to calculate that. I would say from the top your C force can be calculated somewhere here at some value of y bar equals to 15.534 plus 2 times 0.552. But your value of 0.552 is in negative diagram. It's because its value is negative, so I have to keep the negative also. 0.552 because we are calculating the resultant. So there is a difference between 15.534 and there's a difference between this value of 0.552 and one more value of 0.55 that's in this direction. So there is a difference. This is not the same, so we have to calculate this resultant in this way. Then 15.534 plus minus 0.552 and into multiply that total left was your 900 and you divide by 3. So you can solve about that resultant. 15.534 into plus 2 into minus 0.552, okay, divided by sum of those 15.534 minus 0.552 and into 900 divided by 3. So that's 288.9467 from the top. This is the value of location of C force. So total was 900. That means from the neutral axis total up to the top is 450. That is d by 2 is 450. Okay, and we have the value of that centroid of C force somewhere here. C force location, thrust line, C line. I can say this is C line point, P line point. This is thrust line point. Okay, this is pressure line point. Then I would say this is the line of action of that C force, and I want to say what is this EC value. Is this equals to 450 minus y bar, and I can calculate that value is equals to 161.05 millimeters. I want to see whether this was your actual calculations also based on. We can approximate it equals to 161.06. So can we see that? What was your calculations based on? What was your value of EC from this part? Was your value of EC also 161.06? So this is the concept here, 161.06. This is also 161.06. And that's your line of action of that C force. And total C force, we can also say what is the total value. I would say average stress into area of the cross section. Let's solve that. 15.534 and plus minus 0.552 divided by 2 into area of the cross section is B into D, 0.9 into 0.6. This is your area of the cross section. You can solve for that. 15.534 minus 0.552 divided by 2 into 0.9 into 0.6. So you got some value of 4.0451. That means 4045 kilonewton. So this is also equals to P cos theta. So C force is equals to P cos theta. Okay. Thank you for watching that. Okay. Let's go for a general part. We have already touched this. Let's go for a little bit of that. Let's say this was your cable, the beam with some UDL, and we have a cable such that it's having some eccentricity of E1 and E2. Here we have E1, here we have E2, such that neutral axis is somewhere here. I want to take a section somewhere here at some x. I want to say what is the value of what is the eccentricity here, EP. This is some eccentricity EP, and if I take that entire bigger parabolic part, I would say You have this bigger parabolic part. It's having some value of E1 plus E2. That we represent as H, E1 plus E2. And the E1 is constant throughout. Let's say this is value of E1. And I am saying that this is the EP value we have at particular location of X. At the particular location of X, I am having this value of EP. Can you tell me what is this? How can we solve this one? How can we solve the EP value based on the parabolic equation we have? If the origin is at the end, if this is the origin, if this is the origin, I would say, if this is the origin, I would say, we are going to take the origin as this point. We are going to take this as your origin. So I would write equation of 4h xl, or we can write lx minus x square. 4h lx minus x square divided by L square. This is your equation of that particular value of y. And we also have y dash, that is tan theta slope. So that is 4h by L square, L minus 2x. And if I apply that condition, that at the value of x, I need to calculate EP. At the location of x, I need to calculate EP. So your value of y, I would say value of y is actually this one. This is the value of y at that location of x, because your reference origin is here. This is our origin. So your value of y can be solved as E1 plus EP is equals to 4h L into x minus x square divided by x L square. So your different on that particular value of x, you can get the value of EP from these calculations. So you can get the equation for that EP. So get the EP value, get EP, and accordingly we can use the stress method. Once I got the location of that, I would if I use the stress method, I would say this is your P by A, this is your PE by Z, and third one is that we have one more, that's M by Z, and we have to see whether we have some component, whether this is P or this is P cos theta. I think this should be P cos theta. This should be P cos theta. This should be P cos theta, but we generally assume that P is almost equals to P cos theta, so we can either keep it or we can ignore it, P cos theta. So everything is okay, and we need to take that moment at that location x, bending moment because of external loads. That's easy to calculate, no problem with that. And similarly, by the stress method for this problem, at that location, I would say your lower arm would be your moment at that location x divided by the Prestress force of P you are applying on the rod, on the tendon. So Z we got. After that, we can compare that Z versus what you call as EP. At that location, what we got EP, and we can say what should be the value of EC. And after that, I can draw the diagram that, let's say the EC was above the neutral axis, so this is your EC. So diagram is C by A, and second one is that CEC by Z, and that's all from the strength method, CEC by Z. So only two diagrams we have to take. And if this is clockwise, if this is positive moment, so top compressor, bottom tensile. And third method is that load balancing. And load balancing corresponding to that would be you have some eccentricity, you have the eccentricity of that cable throughout the length, such that it's having some eccentricity of E1. This eccentricity we have to keep it as a constant value throughout the length. So the cable would be formed in this fashion, and you are having some external load, and there is some balancing load also. There's some balancing load of 8p h cos theta by L square, where your value of h is E1 plus E2, and cos theta can be solved there. And once we got that, cos theta can be solved here. You can see tan theta we got, and after that you can get sin theta cos theta. Okay, this is the equation for that slope. Okay, so after that, then we see what is the net value of the that UDL. Either it's upwards or downwards. Accordingly, your moment is either positive or it's negative, and your diagram would be this one, or it can be this one. So accordingly, we can calculate the stresses. Finally, let's say the eccentricity was below the neutral axis, somewhere here, E. Let's say the eccentricity, yeah, actually here the eccentricity in this case is positive. That's above the neutral axis for this case. For this case, at all points, our eccentricity is above the neutral axis. So your P force is here. Eccentricity is equals to E1. So your stress calculation is positive P by A. Second one is that positive minus plus, I would say this is P cos theta. This is P cos theta E1 by Z. And third one is because of the moments. It can be either this one or other side. So this is moment at that section divided by z, and this is, I would say, this is the net moment, because we have two different loads, two different UDL. One is the downwards external and one is your balancing UDL. So this is the net. I would say this is the net. So it was a general perspective how we can solve this problem by the three different methods. So a parabolic case of the problem. So this you can keep that. Okay. So we have one more. We can take one more problem here. We can take one more problem here. So we have a prestress concrete beam. So we have that prestress concrete beam. Let's take that prestress concrete beam, PSC beam of those dimensions. Let's have a beam of dimensions. So this is your beam of dimensions. This is 500. This is 1000. Depth is 1000, and accordingly our beam is, let's say this is our beam. Let's say this is our beam, simply support beam, and we are having that UDL, live load of 60 kilonewton. This is live load 60 kilonewton per meter, and the total length of the beam is 14 meters. And we need to say what is the stresses at 5 meter section, somewhere here, 5 meter section. We need to calculate stresses, calculate F top, F bottom at x equals to 5 meters from the ends. So this is your section, 5 meter section. Okay, and your data is given that your steel area of the steel strand is equals to 3000 millimeters square, and your stress in those wires is equals to 1600 megapascal. So from that I can get the value of P force. P force is equals to 360s are 16s are 48, so I would say 1400 kilonewton would be the P force. And one more thing is that, yeah, E1, E2 we know. E1, E2. We know that E1, E2 for the parabolic cable. Let's say there is some neutral axis somewhere. Let's say there is some neutral axis, and I want to draw the cable. Let's say the cable is in this fashion. So this is our cable. We're having some force of P that we calculated some value of 4800 kilonewton, some P force, and value of E1 was given to you in the problem that it's E1 120. So E1 is 120, E1 equals to 120, and E2 equals to 240 millimeters. And I want to say what is this value of EP. Now can you get the value of EP? This is the value of EP, and I have to calculate that if this is parabolic, I have to take this as origin. This is as origin, and I would say at value of x equals to 5 meters, at the value of x equals to 5 meters for the length of L equals to 14 meters, I want to say what is this value of EP. So for that I have the equation. Let's write that equation. Y equals to 4h Lx minus x square divided by L square. So I would say y at 5 meters. I think 5 meters. So y at 5 meters is equals to, actually it is actually the sum of E1 plus EP, isn't it? So it's sum of E1 plus EP here. This is E1 plus EP. I would say y at the 5 meters is E1 plus EP, and that is equals to 4 into h. Can you calculate the value of h? What is the value of h? Is that E1 plus E2? Is that E1 plus E2? That's the maximum value we can have in the curve, parabolic curve. Here we have maximum, that is h equals to E1 plus E2. So h is equals to E1 plus E2. That is 120 plus 240. So 120 plus 240, I can keep it as a millimeter. And we have that Lx. L was your 14 meters and x was 5 meters minus x was your 5 meters divided by total L square was your 14 square. So your y at 5 is equals to E1 plus E2, E1 plus EP. That is some value, some answer we got from this part, and I would say your EP comes out to be equals to, your EP comes out to be equals to 210.6 millimeters, and we got this positive. That means it's below the neutral axis as per our calculations. It is below the neutral axis. It's below the neutral axis as per our calculations. So this is our below the neutral axis. That's 200, 210.6 millimeters. Okay. Now we need to say by the three different methods, we need to calculate the stresses at that top and bottom. So this is the problem, that calculate the stresses at x equals to 5 meters by the three different methods: stress concept, load balancing concept, strength concept. Let's go for the first one, that's stress concept. So first method is that stress concept. So it talks about actual AP value, actual value of P force, actual P force. So here we have P cos theta, and actual moments we have at that section M5. So we need to also calculate moment at 5. So let's calculate moment at 5. Can you calculate dead load? W dead is that 25 into 1 into 0.5, that is 12.5 kilonewton per meter, and that means we need to calculate reaction A, because we don't have to calculate for the mid, we have to calculate at x equals to 5. So reaction at A equals to total UDL of 72.5 into length of 14 divided by 2. Yeah, this is the total reaction we can have for reaction A. So once I got the reaction A, let's try to solve. Let's try to solve further. UDL, where is the UDL? 60 plus 12. So 72.5 is the total UDL into length of 14 divided by 2. That is 507.5 kilonewton is your reaction. And I want to say what is the moments at that section somewhere here. So moments at the 5 section is equals to that's equals to 507.5 into 5 meters clockwise, then anti-clockwise of total UDL of 72.5 into L square by 2, 5 square by 2. So that we can solve into 5 minus 72.5 into 25 divided by 2. So that's 1631.25 kilonewton meter. This is our moment at the 5 meter section. 1631.5. That's clockwise positive sagging. So top compressor, bottom tensile. And based on the stress concept, let's go for that. So we also need to calculate that P cos theta. We need to calculate cos theta. And for that we have this equation. That we can get from this one. I can get the equation for theta. I would say tan theta is equals to differentiation of this equation of y. That means I would get 4h L minus 2x divided by L square. So I can get the tan theta. I know the value of h. Was 0.360 meters, and L is 14 meters, minus 2 into x is 5 meters divided by L square. L square is 14 square. So I can solve that. That's 14 square. Inverse of that into 4 into 0.36 into 14 minus 10. So that's 0. So I can multiply 1000. So I can get 29.3878. But this should be the value of tan theta. That means this value should be some value, but so I can solve further again. 14 square inverse of that into 4h into L minus 2x. That's 4. So I'm getting some value, but it's tan theta. It's tan theta. So I got the value of tan theta as 29.3878. But actually it should be, correct. It's tan theta, so it's not having some unit. So it's a tan theta. Sorry. So we got the tan theta. On the top we had meter. This was also meters, and bottom we have meter square. So finally it's a value that we have to say it is 0.0294. Sorry, 0.0294. This is the value we got, 0.0294. And we can say what is the theta. Theta can be solved as tan inverse of this answer. tan inverse of this answer, that's 1.683. That's 1.6833 degrees. This is your theta value. Theta value is 1.6833. So your cos theta can be solved further. So I would say for the stress concept, this is our section at the 5 meter section. We have some neutral axis, and your P force is acting somewhere here at some eccentricity of EP that we calculated somewhat 210.6. This was 210.6 millimeters PP, and P force was your P cos theta. So your stresses would be plus P cos theta by A, and one more stress is there, top tensile, bottom compressive, P cos theta EP by Z. And because of the moment M5, we have top compressive, bottom tensile, M5 by Z. So that we need to calculate stresses at the top and bottom. So let's solve for that. I would say stresses at the top is equals to the value of P force was 4800 kilonewton, 4800 kilonewton P. I would say 4800 kilonewton into that cos theta. You have to substitute that cos into 1.6833, and that we can get cos theta. And this is divided by the area of the cross section. Area of the cross section we have 500 into 100. So I can write 0.5 into 1, that's 0.5 meters square. This is the area of the cross section of the concrete. After that, we have top compressive, top tensile. We have to write negative. Top tensile, that is P cos theta into EP 0.2106 meters, and divided by section modulus BD square by 6. And after that, we have compressive M5 by Z. Your moment at 5, we calculated that was moment at 5 was, what was the moment at 5? We calculated that 1631.25 kilonewton divided by section modulus of BD square by 6. So we can finally solve those values, and I would say stresses at the bottom would be this goes to positive, this is positive, this is negative. So we have to change the sign here to positive, and this one goes to negative, such that your stress is finally top compressive bottom. So stresses at the top and stresses at the bottom is equal to 17.05 and 2.14 megapascal. So this is your stress variation, megapascal, based on the stress concept. And second method is that we are going for load balancing concept. So we have this beam. On that we have that external load, and the cable profile is parabolic. And to convert it as a straight line cable, we should have some balancing UDL also. To make the cable as a straight line, we have to balance the UDL also by some balancing load of 8ph cos theta by L square. Okay, so let's go for that. Second method, that's what you call as load balancing concept. LBC. Okay, load balancing concept. I would take that this beam. I'm going to take this beam. Let's go for that. Okay. So this beam can be converted to a straight line. This beam can be converted to one more beam, to a beam such that it's having some UDL of external UDL of live load plus del load, 60 plus 12.5. So total UDL of external, that is 72.5. 72.5 kilonewton per meter is the external. That is because of dead load and because of the live load. And there is some balancing load also, balancing UDL. There is some balancing UDL, WB. And we are making the what you call as tendon as a straight line, such that its eccentricity is throughout the same, and that value is equals to E1 above the neutral axis. E1 above the neutral axis. So this is the value of this is the value of E1 above the neutral axis. We have this force of P cos theta. We have this force of P cos theta, and it's having some eccentricity of E1 throughout the length. So this is E1 equals to 120 millimeters throughout the length. And this can be further converted into this way. This can be further converted into this way that we have let's further first calculate the balancing UDL. That is 8 PH cos theta divided by L square. Let's substitute those values to get the intensity. I would say 8 into P, 4800 kilonewton into cos theta. We already know that was cos theta. That is cos of 16833. Okay, and your H value was sum of those two. That is 0.36. H is E1 plus E2. That is 0.36. That is 0.36. That is 0.36 divided by total length was 14. So 14 square we can write. So your final value would be that 8 into P into cos of theta, then H divided by L square, 14 square. So you got that 70.5. You got that total intensity as 70.5 kilonewton per meter, 70.5 kilonewton per meter, and it's upwards. This UDL is upwards 70.5, and there is downward of 72.5. So the final diagram would be a downward value of see 72.5 is downwards and 70.5 is upwards. So net value would be downwards to 2 kilonewton per meter. 2 kilonewton per meter, and this what you call as P cos theta can be its effect would be transferred to the what you call as to the neutral axis, such that there is a cable at the neutral axis location, but it's having some moment associated with that, and that is clockwise moment about the neutral axis. Clockwise moment about the neutral axis equals to PE1 P cos theta into E1, and there is some force of P cos theta applied here. So I can finally say that based on the load balancing concept, we can have the diagram in this way now. Finally, I would say you had this section, that's 5-meter section based on the load balancing concept at the 5-meter section. So we have a P force acting somewhere here. We have this P cos theta force acting at the location of E1, so I would say the stresses would be equals to P cos theta direct compressive stress P cos theta by A, and second stress is that because of the sagging moment about the neutral axis, sagging. So this is sagging positive, so top compressive, bottom tensile. That is P cos theta E1 divided by Z. And there is one more thing, that's UDL. There's one more thing, that's we call it as a UDL. Because the UDL is downwards, so sagging moment would be developed. So top compressive, bottom tensile with some value of M5 net, we can call it as M5 net divided by Z. M5 net divided by Z. So we need to calculate moment at 5 location. So we need to calculate moments at this location. So for that, I have to say what is the reaction A. What is the reaction we have at this location? Reaction A, that is total UDL was net 2 kilonewton per meter. 2 kilonewton per meter for the length of 14, but I need half of that. That's your reaction A. That is 14 kilonewton. So your reaction is equals to 14 kilonewton, and into multiple of that 5 meter. That is your moment because of the reaction, and subtract that UDL effect. It had to be subtracted. So your moment at 5 coming to be equals to moment at 5 45 kilonewton. 45 kilonewton meter. Let me check that. 25 minus 14 into 5. That is 45. 45 kilonewton meter. 45 kilonewton meter. So I can write here 45 kilonewton meter divided by section modulus of, we had this beam 500 and 100,000. So BD square by 6. BD square by 6. So I got this stress. I can solve this one. P cos theta, we already know how to get cos theta. Cos theta we know. Theta was 1.6 some value. Cos theta we already know. Cos theta was 1.683 and theta was 1.683 and cos theta we can solve for that. So we already know let's go for that. So let's go for that. P cos theta, I would say your P was 4800, your cos theta is there, divided by area of the cross section is 0.5 meters square, and you had this P cos theta, that's 4800 cos theta. Your E1 was 0.12 meters divided by section modulus of BD square by 6, BD square by 6, BD square by 6, and third is this value. So I would say your stresses at the top is plus plus plus. So stresses at the top is plus plus plus, and stresses at the bottom is plus plus minus minus, plus minus minus, such that the values finally is equals to, finally your stress values is equals to that 17.05 to 2.14, 17.05 2.04, 2.14, 2.14 megapascal, similar to that of a previous case using the stress concept. This is our stress concept, stress variation. And third method we have what you call as strength concept. Third method we have what we call as stress concept. So what you call as what you call as strength concept. Strength concept. So what is the steps we have in the strength concept? So third method is that what you call as strength concept. In that first step is that calculation of that shift of that C line from the cable line, shift of that C line from the cable line. That means where the C force is acting and where the P force is acting. Okay, so that we represent as Z, and that was what was the actual moment at 5 meters section because of the external loads, and divided by what you have, that P force, divided by P cos theta, we can say P cos theta, because your cable is not purely axial, so P cos theta. So Z is M at 5 divided by P cos theta. So we already calculated that moment at 5. Moment at 5 we have calculated that moment at 5 was what you call as 1631.25 kilonewton meters. This was your moment at 5 because of the external loads of UDL and live load. That's UDL dead load and live load. Okay. And your P force we already have P cos theta. Let's substitute those values. I would say your Z is equals to 1631.25 kilonewton meter divided by P cos theta of 4800 kilonewton into cos theta. Cos theta we have some value. Then finally your Z is the value coming to be equals to 340 millimeters. This is positive value. That means the shift from the value of EP, that means at this location your EP was acting here. That means your P force was acting at this location of EP from the neutral axis, but your shift of that C force is somewhere here, such that it is a positive value, and this total value is equals to Z. That means the C force is acting somewhere here. On that particular section we are talking about, and this would be equals to EC at that particular section we are saying, at that 5 meter section. So your EC is the difference of Z minus EP. So your Z is 340. EP was 120. What was the value of EP at that location? EP was 210.6 millimeters. 210.6 millimeters. So your AC is positive. That means it is above the neutral axis. It's positive. That means it is above the neutral axis. 129.4. So finally, I can solve now your section at the 5 meter span, at 5 meter section. This is 5 meter section having the dimensions of 500 and 1000, and neutral axis is here, and C force is somewhere here at some eccentricity of EC. C force. So your diagram would be C by A, and one more diagram would be, because of the moment it develops, that's positive sagging moment it develops about the neutral axis. So positive CEC we can write. So top compressive, bottom tensile, CEC by Z. where your C force is always equals to P cos theta for this case. C force is equals to P cos theta. If the cable is not purely horizontal, if the cable is having some curvature or bent, it's bent, so it's we write C force is equals to P cos theta. So accordingly, I would say your stresses would be that finally I can write the equation. Your C force is equals to, your stresses would be F top equals to positive C by A, that means P cos theta divided by A, and plus C EC by Z, that is also P cos theta EC by Z, and that we can say P was your 4800 and cos theta we know, and divided by area of the cross section, plus P cos theta 4800 into cos theta into eccentricity EC. What is this EC? 129.4. So we can write 0.1294 divided by section modulus BD square by 6, BD square by 6, and you can get the values. This is your top, and that is top value is 17.05 megapascal, and bottom value is difference, this minus this. So bottom is, we already have that value, 2.14 megapascal. Again, that same stress variation. So this was a beautiful problem. Okay, this was a beautiful problem. Now we can take that, we can take one more problem that's having point loads at third points. Let's go for that. Let's go for that. It's saying that we have a cross section 300 cross 800, and the beam is such that we have two loads of 20 kilonewton at the third points. Total beam is 9 meters. Simply supported Prestress beam, and it's saying that you have to suggest a cable profile. You have to suggest a cable profile. Now you tell me which cable you should suggest for that. Suggest a cable profile, and yeah, I would say a cable profile is designed in such a way such that it's similar to that of a BMD because of the external loads. So your BMD, because of the external loads, actually a diagram that's in this fashion, a trapezoidal form with this value of peak value of PL by, that's P into 3, that's 60 kilonewton meter is the maximum value of that external loads. So I would say I would suggest what you call as cable such that its shape is similar to that of this one, and its diagram would be reverse of that, such that it counteracts the effects because of those external moments. So this should be my profile of that cable with some eccentricity E at this location. Eccentricity E. Now we need to say the problem is after that going to start that. So first part is over. Okay, it's saying that for eccentricity of, for E equals to mc square, for E equals to 100 millimeters at the mid third portion of the beam. Now once it's saying that mid third portion, that indicates the cable profile is in the form of trapezoidal. That's in the mid third part of the beam, we are having the cable having same constant eccentricity of 100 millimeters. Okay, so we need to say get the P required. What is the P required force, Prestress force required to balance the bending effect of external loads, that is W. Let's say there's these W's, we can call it as W. Because of these external loads, we have to balance the effect of those. What should be the value of P such that it can balance the loads, external loads? And you have to neglect the self weight. It's saying that we are not applying any live loads. we are applying only, let's assume we are applying only point loads, and let's forget the live load, that what you call as self weight. Self weight we can ignore for this case. Let's ignore the self case for this case. Self weight ignored. So for E equals to 100, okay. Now I would say the diagram would be some sort of trapezoidal shape for the cable, such that it's having constant eccentricity along for the mid third part of the beam equals to 100 millimeters. So this is your 100 millimeters. E equals to 100 millimeters. Now it's saying that what should be the value of P? What should be the value of P? How much P should I apply such that those W's are balanced? The effect of those W's is balanced by that load at that particular section. So I would say that your W should be equals to P sine theta, as that of a, we have already studied the load balancing concepts. So I would say W should be equals to P sine theta. If this is theta, I would say this is W should be equals to P sine theta, and we can say your sine theta is equals to tan theta for small values of theta. So that means we can solve that. P required is equals to, what is the value of W? 20 kilonewton. So I can say P required equals to 20 kilonewton, and your tan theta is equals to 100 millimeters divided by length of 3 meters, that is 3000 millimeters. 3000 millimeters, this is your tan theta, and we can write that that's 100 by 3000. Yeah, this is inverse of that. This should be inverse of that, that is 3000 divided by 100. So finally you got 3 to the 6, 6000, is it 6000 kilonewton? 600 kilonewton. So P required is 600 kilonewton. So you have to apply this amount of force such that your bending stresses, because of the external loads of W, that are balanced by the effect of that P at some location of E, such that it counteracts the effect of those external bending stresses. So that's what we have here. That's W equals to P sine theta. W equals to P sine theta. Okay. Then one more thing is that find the P required if the resultant bottom fiber of the mid span section, because of the self weight, live load, press stressing force. So second part of the problem is, second stage of the problem is that now for P you need to calculate now also P required to balance yeah, for let's take the problem. I would write the problem. Find the P required. This is the second case of the problem. Find the P required if the resultant stress at the bottom fiber of mid span section this resultant is because of all those effects. One is your dead load, that is self weight, dead load, live load, P force, it is eccentricity, all those effects we have to say. The resultant diagram of that, let's say the P by A is this one, and PE by Z is this one, and because of the dead load we have this one, and because of live load we have this one, and net diagram should be such that your stresses at the bottom is equals to 0. I think it's saying, yeah. I think it's saying we need to say total such that stresses is 0. I think it's saying we have not properly written the problem. I think it's saying that we have to keep the bottom fiber stress equals to 0 finally. So such that final stress would be diagram would be in this way, that stress at the bottom is equals to 0. Let's try to calculate the stress at the bottom to be 0. So for that case we need to calculate what should be the value of P that is applied on this cross section at some eccentricity of the mid-span section. See, once your E is fixed, your value of E is fixed, okay, your E is already known to us, that's 100 millimeters. That's the profile is in this way, and we have to calculate that at the mid-span section of the beam. So at the mid-span section of the beam, so let's go for that. Your P force was initially 600 kilonewton required, and we need to calculate for the second case. So we need to first calculate the dead load, because we have to calculate all those effects. Dead load would be equals to 25 into 0.8 into 0.3. That's dead load is equals to 24 into, we can solve it for 24 because we have calculated it for 24, so we can take 24 into 0.8 into 0.3. So that's your 5.76 kilonewton meters per meter. So this is your dead load, and because of the dead load, moment at the midspan is, I can say that's MD, that is 5.76 L square by 8, L square by 8 into 81 divided by 8. So that's 58.32. That's clockwise, positive, positive clockwise. Okay. So sagging moment, top compressor, bottom tensile, and because of what you call as, because of these point loads, our diagram is a fixed value having 60 kilonewton as the maximum value, and that value is constant throughout that middle third part, 60 kilonewton meter. So we can add, this is positive stress, and this is also positive stress, so we can add. So I would say moment all is positive, that is 58.32 plus that initial value 60, so it's 118.32 kilonewton meters total moment that's applied, that's positive. So top compressor, bottom tensile, top compressor, bottom tensile, top compressor, bottom tensile. But we need to say, we need to calculate the stresses at the midspan. Yeah, this is the first case, this was the first problem. So we need to calculate on the bottom fiber of the midspan section, that resultant should be equals to 0. Let's say resultant should be equals to 0. Resultant stress at the bottom should be equals to 0. So we had this condition that stresses at the bottom should be equals to 0. And let's have the effect of P and E. Let's have the effect of P and E. So let's say that P at this location. Can you tell me what is the what's the eccentricity at this location? So we need to take a section at the midspan. I would take that section. It's having some eccentricity of E equals to 100. So let's have that section. So this is your section. Neutral axis is this one. P force is acting here. Eccentricity at the midspan section, that's 100 millimeters. No, now we can solve further. So will there be P cos theta, or it would be P sine equals, is this P cos theta or it's only P? Tell me, is it P cos theta or it's only P? I think it should be P cos theta only. It should be only P. At this location we have a straight line here, so we can treat it as a P value. We can take it as a P value here. So I would say the stress, first stress is that P by A. Second one is that hogging moment, so negative to top tensile, bottom compressor, P 0.1 by Z. Third one is that because of the those moments, because of the dead load, live load, we have M all by Z. We have calculated that M all 118.32 by Z. That's your equation. And I'm saying that my stresses should be equals to 0 at the bottom fiber. So I would say at bottom should be equals to 0. That is equals to P by A. That plus P by A plus P PE by BD square by 6. And we have minus M by BD square by 6 equals to 0. So equation we can have, a general equation we can write. Your BD is here also, P by BD. So BD goes outside, BD goes outside. From this side, from this one, we can also say BD goes outside. And from this part also, we can say BD goes outside. So you're left with P 1 plus E by D. And that is equals to M. And we have 6 left here, 6. So 6M by D. So we can substitute the values. I would say P required is equals to, your moment was 118.32 kilonewton meters, and multiple of 6 divided by that depth of D. What was the depth of D? That's 800 millimeters. That's 800 millimeters. This is your value here, and we have to divide that this part. That's 1 by 6 times eccentricity was 0.1 divided by D is 0.8. And finally, I would say your P required force is equals to required force is equals to 507 kilonewton, 507 kilonewton, 507 kilonewton, 507 kilonewton. I think we have one lost problem left. I think we have one lost problem left. So we need to check that. Let's go for the final problem. Let's go for the final one. Final problem we have. So we have 8-meter beam. We have 8-meter beam. 8-meter beam. And simply supported. Simply supported. Live load plus dead load is there. Live load is there. Dead load is there. Live load, dead load is there. Let's write it as external load is equals to live load plus dead load, and that is total equals to 1. I would say that is 1.57 plus 2.50. That is sum of these two is this much kilonewton per meter. And we have this area of the cross section is a I section. We have this beam of I section. That's cross section is I in the shape of I. So we have this section, and the top dimension is 250. The flanges are thickness of 80 millimeters, and it is symmetric. So neutral axis is at the mid section at the CG, and CG is at the mid section. So your neutral axis is this part. This is your neutral axis, I would say. And the force and the cable is placed at some eccentricity from the neutral axis. That is a value of your eccentricity from neutral axis is what you call as 150 millimeters. 150 millimeters. That's the EP. Now total dimensions is provided that we have total dimensions of 450. Total depth is 450. Now can you tell me based on this, what is this part? What is this total value here? Is it 225? Is it 225? And if this is 80, I would say where is the location of that 150? So I would say 225 minus 150. 225 minus 150. So it's 75 below the from the bottom. It is at location of 75. So from the bottom it is at some location somewhere here. That's it's here at some location of 75. Based on that, because this is your E. E is equals to 150 millimeters. Eccentricity of that P force, or we can say cable is located at eccentricity of 150 from the neutral axis. Okay. And moment of inertia is also given to you of this cross section. We can solve that still, but it's given to you 1.553 10 to the power 9 millimeter power 4. And we need to say get the effective force in cable, and there's some cable provided, and we need to say get the effective force in the cable. Get the effective force in the cable. Effective force in the cable. In the cable for balancing the dead load and live load. For balancing dead and live loads. So cable is also provided to you, but it's saying that get the value of P. Get the value of P. Let's have the cable. Let's have a different color. So cable is here. It's a bent cable, I would say. The cable is a bent cable. Cable is bent. Cable is bent. Cable is bent cable. Okay. Now the P force is applied here at the neutral axis at the ends, and some eccentricity is there at the mids. Eccentricity of E equals to 150 at the midspan section. So this section that we are showing, it's of the midspan section. This is for the midspan section. This is the E. And the thing is that we have to say what's that value of P such that it's going to balance the dead loads and live loads. Effect of those. That means the moments contributed by those, that means the moments because of the dead loads and live loads, that should be counteracted they are going to create those stresses, bending stresses, that should be counteracted by that force of P and its eccentricity at that location E. So I would say to make it as a straight line by the stress by that load balancing concept, I can make it as a straight line. I can make it as a straight line. I can have a straight tendon, and there is some balancing load. So balancing load of 2p sine theta at this point. So this is your final diagram for the problem. There is some external load, and we have this cable of P cos theta here, and eccentricity is 0 for our throughout the length. Eccentricity is 0 throughout the length. And there is some balancing load of 2p sine theta for this cable, 2p sine theta. And if I say sine theta is almost equals to tan theta, so you can check that also. 2p tan theta, we can write here. 2p tan theta. And from this triangle, you can calculate tan theta. Tan theta. Tan theta is perpendicular by base. Your 8-meter beam is there. That means your base becomes 4,000 millimeters. 4,000 millimeters. And still, if you want to calculate sine theta, you would see what the difference is there. Sine theta corresponds to 150 divided by 4,000 square plus 150 square. You can say that if this is theta, this is theta. So if I solve sine theta first, I would say what is the value of sine theta? 150 by root of 150 square plus 4,000 square. So this is 0.0375, 0.0375. And if I want to solve by the other one, that's 150 divided by 4,000. That's also 0.0375. This is also 0.0375. So both values have the same answer. Both values have the same answer. 0.0375. 0.0375. And I would say that balancing load is equal to 2p sine theta. And what is the value of p? I don't know, but I know value of tan theta, and I have to multiply that with 2. So finally, I would say this value finally coming to be equals to, this part is equals to 0.0750 into p. And its equation we already know. That this was all we studied that load balancing concept. If we have point load, and if you have that particular load, and there's an external load, because of that there is some moment m, and there's some m, and we have this bent cable. At the midspan, we have some eccentricity. I said that E is equals to PL by 4, and there was some moment of this was your PL by 4. That's moment at that section divided by that Prestress force. This was the equation actually, mx by p. This was the actual equation, mx by p. And I know the value of E at the midspan. I can say what is the moment at the midspan. That already we also know. So I can get the value of P. So if I solve for the moment at the midspan, can you tell me? WL square by 8. So that would be, so if I solve moments at the midspan, that is WL square by 8. So moments at the midspan, that is equals to WL square by 8. That's 1.57 plus 2.50 L square by 8. And this is your moment at the midspan, that is equals to 32.56 kilonewton meters. I would say E equals to m mid divided by P. So your P required is equals to, your P required at the midspan, that's P required is equals to m mid, that is 32.56 kilonewton meters divided by eccentricity at the midspan, that is 0.15 meters. So your P required is equals to 217 kilonewton for complete balance of those external loads, for complete balancing of those loads, complete balancing of those dead loads and live loads. Okay, so we also have to solve that stresses at the midspan section. Let's solve now. Once I got the value of P, I am going to solve now stresses at the midspan section. So once I have completely balanced the effectors of those dead loads and live loads, now second part of the problem is that now you need to calculate stresses at the midspan section. So I would say there is some section at the midspan, and P force is acting somewhere here, at some eccentricity of E equals to 150 millimeters. This was provided to you, and the section is actually a rectangular section, this I section. So we don't care about that section. We can directly solve. Section is symmetric, it does not care, it does not worry, it does not have any effect here. If the section is symmetric, we can directly use it. So I would say your P force is acting here at the midspan section at some eccentricity 150 millimeters. Okay, 150 millimeters. And I would say the stress diagram would be, first value would be P cos theta. Yeah, it would be P cos theta. That means this force is P cos theta. So I would say P cos theta divided by A. And second diagram is that I want to check what are the values of other those effects. So because of this P cos theta into E, you have hogging moment, negative diagram, top tensile, bottom compressive. That's P cos theta E1 by Z. And similarly, third one is that because of the moments we have applied at the midspan section, that was M all by Z, M all by Z, M all by Z. Now, can you tell me what's the net value we can have? What is the net stresses we can have at the midspan section? Because we have completely balanced that external moments. We have balanced those external moments at the midspan by that value of P at some eccentricity E such that your stresses at top is equals to stresses at bottom equals to 0 because of that individual effects. So I have completely nullified this effect. If I solve this part and this part, I want to see what the value comes out to be equals to. I want to see what the value is coming out to be equals to. I want to see what the value is coming out to be equals to. Yeah, actually we had to write this the equation we had there. The equation we had there. Actually we had to write there. It was actually in this way that this was your P. So we can actually write cos theta here. We can actually write P as a P cos theta. But still P cos theta can be ignored. So if I still say that E equals to mx by P, E equals to mx by P, and cos theta, if we see what is the value of cos theta, I would say cos theta is almost 1. So we can ignore for this part. To get the rid out of that, I would say cos theta is almost 1. Sin theta is 0.03. Is that sine inverse of that? Let's wait. 0.0375 cos theta. See, the cos theta is 0. See, the value of cos theta is 0.9993. So that's almost equals to 1. So if we can ignore that part, okay? We can ignore that part. Let's ignore that part. So cos theta we can ignore. So I can write it as P E1 by Z. And this one is your M all by Z. But what's the value of E? What's the value of P we got? Can you tell me what is the value of P we got? 217. So 217 and eccentricity is 150. Z is same. If I want to say what is this value and what is this value, is this equal? I want to see whether this is equal. And this is your MA by Z. The moment MA was what was your moment at because of the all loads? Moment A, you calculated that as 32.56 kilonewton meter, 36.52 kilonewton meter. So your moment was 32.56 kilonewton meter divided by Z. If you want to you want to check that whether this part and this part is same. This is in millimeters. This is in kilonewton. So you write that 217 into 0.15. So that's also 32.55. So approximately equal. So that means the stress is by the definition of completely balancing the effects. That means we have completely eliminated the effect of this stress. If there was some stress here at as sigma 1 top, we finally make it as a positive here because of that moments, such that the net because of these two is 0 at all fibers of the beam. All fibers of the beam we are having one of the value is positive, other value is negative, such that they are completely balancing one another. That is the definition of that complete balancing of that loads. So finally your stress diagram is only at a rectangle that's having a constant stress for all those fibers equals to P cos theta by A, and that P cos theta by A we can say that's that is equals to P by A. So stresses is equals to P by A for all fibers of that midspan section, and that is equals to, your P value was 217 kilonewton by cross section area. It was given to you area cross section, so I would say 217 kilonewton by area cross section of the I section. I section was given to you, the area of the I section. Area of the I section was given to you as 0.063 meters square. 0.063 meters square. So you can add 0.063 meters square. So your stresses, that is 3.44 megapascal for all fibers along the depth. That's constant stress. So final conclusion is that once you completely balanced the stress external loads, by completely balancing the external loads, your stresses is only, your final stresses is equals to only P by A. Your only stress that is acting on this section, that is equals to P by A, because your M by Z has been balanced by PE by Z. Here we have negative, and bottom we have positive in this side, because we said that M is equals to P times E, because we said M equals to P times E for all those cases. Okay. And one part of the problem is that, the third part of the problem is saying that you calculate the shift of the P line, pressure line from the tendon line, or we can say cable line. This is your tendon, or we can call it as cable line. Shift of the P line from the cable line, I would say that is equals to E. Yeah, that's equals to Z. That is equals to moment at that section, moment at 5 meters. I can solve for the midspan. Moment at mid divided by total P, that corresponding to shift at mid. So Z is a function of location of X. So moment at mid, we got the moment at mid was, we have calculated that moment at mid was 32.56 kilonewton meter divided by P. The value of P was, we got as 217. The value of P was, we calculated that as 217 kilonewton, and your value of Z would be equals to 150 millimeters. So what that means, we are going to see that. So your 150 millimeters, that means what? So your shift of 150 millimeters, if this was your cross section, your P force was acting here at some location of E equals to 150 millimeters. I would say C force was, now C force I calculated that is acting somewhere here at the location of Z, such that the Z is also equals to 150 millimeters. That means C force is acting at the centroid. C line acts at centroid. C force acts at the centroid. Or neutral axis. So your C line is at the neutral axis for the midspan section. Yeah, I think it would be, and for all values of X, for all values of M, it would be same value. It would be having same value. It should be having same values. If I try to calculate, let me try to calculate at a particular value. If I try to calculate at this value, at this location, I would say moments here would be equals to reaction. Let's forget that. So your C force is acting at the centroid. I would say because your stress was constant throughout the length, throughout the section. Your stress was throughout the section depth of D. It was constant stress of P cos theta by A. So your centroid is acting, C force is acting at this centroid, at the neutral axis. That is the definition here it means. So thank you for watching our lectures. That's your stress concept, strength concept, and load balancing concept. Thank you very much.